Okay. Hello everyone. How are you guys doing? Am I loud and clear? Awesome. Okay. So, what are we going to do today? Deep learning, deep learning, deep learning. Okay. It's going to be very interesting session today. I hope. And I'm almost sure that we will not be able to finish what we'll have to divide the session into two. If, but that's okay as long as we understand it well. So, what are we going to do? So we will actually be doing, so we'll be doing recurrent neural network. In fact, let me just give you this link. Can you guys download this link as well? The data set, I don't know whether you have the data set or not. Let me just share in the chat. Yeah. So please download this data set. This is as a part of your one of the unassisted practice of Jupyter Notebook. You would need this. Download it and upload the zip in your practice lab. Okay, and just keep it ready so that we can start using it. So before we do anything, have any of you started your projects? Did any of you attempted at least any of your projects? I was thinking that we can actually discuss maybe like, end of the session, 10 minutes, 15 minutes, not more than that. How the projects are going. Okay. We can do that. Um, but let me know if any of you have started the project. A yes or no would do for now, and then we can actually deep dive to if you have. Okay, awesome. Yeah, I've got a one yes, right. Okay. So what are we going to do? What is today's agenda? We finished convolutional neural network yesterday, and we've now a pretty much good idea of how you can build, how you can model intelligence inside a machine, isn't it? All these large networks that you see, all these heavy-duty vision networks, we now understand. Anyone can give us any kind of a complicated architecture. We probably will not be able to understand all of it because for that we have to, go through the advanced computer vision, topics. But at least we will be able to understand a lot of things about vision and its own core components, isn't it? Today we will start a little, one more style of network that is rather important in many of the aspects, which is called as this recurrent neural network. Okay, and it's used in many places. We will be focusing only on, I don't think only, but most of the time we'll be focusing on the time series aspect of it. Even though you have one practice session on something from a sentiment analysis system, okay, that which is nothing but an NLP application, isn't it? We will see that how it is done. I have run all the three things except the unassisted one seems to be running fine. So we will see whether if we have any issues or not. Any questions, any comments before we get started on RNN? Anything that we want to talk? Any confusions that you have? Anything that is fundamental that you want to clarify before we move to a new topic? This is not a brand new topic, but yes, the style of solving things will be a little different. But you will have the same flavor of things. You will have your weights and biases. It's just that your final functions will be little bit more. Any questions, folks? Okay. Then let's start. Okay. Let us start on the our idea of what is recurrent neural network. Okay, so we've looked at we looked at one of the we looked at CNN yesterday, the core component which does you know feature, which basically his job is to actually generate features from an image, right? Convolution operation is not only specific to image, but it works beautifully for image, and there are a lot of tools that has been built over the years to ensure that the CNN or the convolution part of it or the convolution neural network works good for images, right? By filters, by and then we will when you go deep into computer vision, you will see that there are tons of tricks, and to that helps to ensure that it can actually generalize for all kinds of images, not just some sort of not just there can be many types of complicated images in the world, right? So we will move to this idea of something called as a recurrent neural network. So what are we trying to achieve by after this session? We will try to understand that how do we implement RNNs for our recurrent neural networks for something called as sequential data. In fact, before that, we will try to understand sequential data. Anyone here wants to tell what is a sequential data? How do you define a data which is sequential in nature? We will go through that. Okay, but I think that is a good in understanding a starting point, that what is a sequential data. Okay, um, how do we model a sequence data? What does it look like? Okay, what's its traits? Okay, we will see that there's a flavor of RNN, which is nothing but this algorithm called as LSTM. Okay, how it learns, how it tries to improve on some of the things that the vanilla RNN has given, and then it tries to mimic the way we probably try to learn, right? And we will try to see and improve LSTM using again a variation of it called as gated recurrent units, or GRU. And we will see that we will end the topic with a light discussion on this idea of attention. You should understand that the last one, okay, I think it has now changed the whole entire landscape of things, because attention based frameworks are left, right, and center. In fact, they are so awesome that you might not even need recurrence, okay, in language models. Okay, that's what they said. In fact, if you might have heard, right, BERT, GPT-2, GPT-3, okay, all these large language models. There was a language model which Hugging Face built, Bloom, open source yesterday, right? They've launched it yesterday, and you can try it out. um, Again, everything is an attention based transformer architecture. Okay, so here we will just touch base, just get the idea what it is, and that's about it. But attention is very, very important too, for us to understand. Okay, I hope we are clear on the learning objectives. Let's start. So what is sequence data? A sequence data is nothing but a data set which is said to be sequential in nature, isn't it? Where data points are dependent on one another and it's not unique. So and there basically there is some sort of dependency, right? Did we till now work with sequence data? Suppose, do you think MNIST is a sequence data or data set? Why not? Why do you think MNIST is not a sequence data? You can say, right, it comes after 1, 0 after 1, after 2, after 3, right? So after 0 it comes 1, right? So after 1 it can come 2, right? So did you treat sequence MNIST as a sequence data? We did not, right? We've treated each of those images on its individual merits. We did not say that just because there is a 0, there has to be 1 the next one, right? So essentially MNIST, though a number series might be sequence in nature, the way we dealt with the MNIST problem was not at all sequential, right? It was on its own independent image identification, right? Till now, whatever the diabetes test case that we did, the diabetes data set, do you think that there is any sequential component into that data? No. And why do you think that it is? Right? So because there is no order, there is nothing connecting, there is nothing connecting one sample to other sample, isn't it? Did two sample, was there any sort of relationship? All we are trying to do, we are trying to build relationship between our X and Y, isn't it? That's all we are trying to do. Our whole game of machine learning is about X and Y, which is basically from the same sample itself, right? How is my 8 features of my same sample relates to my ninth feature of the same sample, and hence in so many number of features. We never discussed that, okay, my sample number 1 also is somehow dependent on my sample number 2, or the other way around, right? That's that is what it is, right? So at a very raw level or a low level, you have now sort of established some sort of relationship, and in case of time series, it is the relationship is nothing but time, right? If you see, this is a stock market price trend, right? We will see that the stock is going up and down. People who are from finance or even trade, they understand that, right? Time as data, or time as a feature that you have to imbibe. Time versus data, or time is also a feature, right? So whenever you trade, right, you generally look what was its trend 2 3 days back, isn't it? That is so common, right? But why are you looking at 2 3 days back? Who's stopping you to look at 2 months back? Who's stopping you to look at 20 years back? So people do it, right? Whoever are, deep traders. But our objective is to understand the pattern. Against what? Against the time, right? So the time is the component, but do you think that whatever trade that you did yesterday has anything to do with whatever trade that you are going to do? These two trades are independent in all its true sense. Right? There is literally no connection when you do the actual trades. But when you try to find the pattern, you are trying to make a pseudo connection between them by this feature called as time. But how will you model this feature called as time? Time is just some, like, at 2 o'clock it was this, at 3 o'clock it was this, or this day, this day, this day, this day, right? So that's one of the things. So that is one way of looking at sequence data, isn't it? What is the other way of looking at sequence data? Weather pattern. Somewhere was telling, right, weather, right? We know that we have some, I don't know whether this is true or not. If you are in London, it will never be true. Okay, I don't know if how many of you have been to London. It's never true, right? It's always rain, and just like all over across. Even in the place where I'm at, right? Morning it will be sunny, in afternoon it will rain a lot, right? So point is that there is, however, like, okay, if it's hot in the summer month, it is hot. Generally, most of the days it will be hot, right? But that seasonality aspect of it, how will you actually build into feature? So you can say that no. What I'll do is, like, I'll put a feature, tabular feature called as season, and then that's how I model it. But then there will be some sort of outlier, isn't it? There is sudden monsoon shower in between summertime, and we have seen that over a historical period of time, that particular week always has some sort of shower. But if you actually transform into tabular, you might actually miss it. So it's to build any kind of intelligence. Why only neural network, right? We would need to actually, have some sort of norm around it, right? So before we go to down, let's go to our, let's talk a little bit more on the. So I've just gone to our Scribble, okay, our Scribbler, our explainer, and so if this is my sequence data, let's evaluate this. What is our sequence data is, okay? So this is a problem, okay? This is my data set. This is a data set that we are very familiar with. What is this dataset about? It's a very simple dataset. All it says is that day-wise number of guests in a five-star hotel. Okay, and the manager of that five-star hotel has hired you because you're a data scientist, right, and a machine learning engineer, and if they want you to model, trying to find out, okay, on the day 11th, the multiple questions that he's asking is that, can you tell me on the day 15th day of the month, what will be my guest? Or this particular week, on the third week of my month, what will be my guest? In the month of December, how many guests? What will be my guest? And then what will be my count of guests, right? So now you will, from a machine learning standpoint, you will say, okay, this is a regression problem because output is actually a number. But then you will be in a problem that how do I, if I have been given this tabular data set, what will you do? How can you even, so the question, so you understood, right? So this is the question, and then basically he's asking you, what is he asking you? He's asking you that on suppose day 15, what will be my guest, right? So this is the question that he's asking you. So how will you solve it, right? So this is clearly a sequence in nature, right? There is a sequencing, right? Day one has happened, and after that, day two has happened, and day three has happened. Maybe on the weekdays, on the Fridays, there's heavy. You can put all these features manually, isn't it? You can get a restaurant guy, say that from Friday to Saturday, the numbers will be high, and everything else, the numbers will be low. You can add more features to it, but you will still be missing this time component or this sort of an ordering component that is happening, which needs to be presented, right? Do you think that, how do you want to solve this thing? Can anyone tell me before I actually reveal the answer? I think I've already revealed the answer when I've shared the screen. How do I want to solve this thing? If you have been given this problem set, people who have done time series, they can easily answer. If I have to do this, what will I do? Think about it. Average of what? Okay. But if I do average, what will I do? Average. Okay. So good question. Good point. If you do an average, what happens? You lose, right? What you are losing quite a bit of thing. And if you have an outlier, one of the days, if you have an outlier, you are gone, right? Yeah. So moving average, of course, right, right. So it's, yeah. So basically, moving average. How do you build moving averages? So the answer is moving average. Absolutely, totally. From a data standpoint, so algorithm that is going to use in some sort of moving average. Absolutely. But how do you calculate the moving average on a data like this? I'm starting from the place of data and then I'll come to algorithm. You are describing an algorithm. I'm trying to find out how will I even calculate the moving average on a tabular data like this? I have been given this. I have not been given a sequence data. Do you think this is a sequence data? This is not. No, you can medium, mean, but you're gonna cut some information, right? How will you even do though? How, even if you in any kind of, more mean mode, medium, any kind of, you know any kind of those things will actually lose values, right? But seasonality or this time seriousness, you will need to. So whatever is it, we x to build a model, we know one thing. Whatever model we want to build, we need our features, we need our representatives, right? We need to know what will our features be, and we must also have the target variable. We have to somehow transform this into a supervised learning problem in such a way, right? In such a way that we can actually understand it, and then that way is nothing but this, and we will actually try to represent the data as a sequence. Okay, right? So now this is what I do. Okay, I will transform my data into this. Okay, now you will see that my x is what. Okay, so this is very fundamental. Okay, if you have done time series, it's okay. So this is exactly what a moving average does, right? If you want to use a moving average, you have to give a bunch of values in a list. So my x is nothing but this list. What I am saying is that if 250 and 243 and 251 happens, my y is 252. Do you agree to this x and y fact? Are you able to understand this part? Think about it. Are you able to understand this fact? If 250 and 243 and 251 happen, continuously, right? So I'm creating a list. I'm saying that if 250, then 243, and then 251. This is an ordered list, right? This is a clear-cut ordered list. I'm saying that this is my x. Then in that case, y will be 252, right? I've taken a slide of suppose 3. Okay, you can take any side of slide, right? Slide means that I'm going to consider, all of three elements together, and I'm going to put a y. So I can transform my data set into this, right? Anyone has a question? Are you able to understand it? Understand this idea? This is how we actually do time series, right? How we do time series? We will change from a tabular to a. How did we arrive at 250 to 42? Because this is the sequence. This is a sequence, right? In day 1, 250 happened. In day 2, 243 happened. In day 3, 251 happened. And in day 4, 252 happened. This is actually there's no significance. You can do whatever. 3, 30, 43, 1, 2, doesn't matter. Okay. That number doesn't matter. Okay. That is just up to you. How long you want to do. Okay. I just taken 3. Doesn't matter. So you can take any k. Yeah. It's just like some k. Okay. So if 1, 2, 3 happen, I know for sure on the 4th day 250. This is hard fact, right? So I am transforming this into a time series or in a sequence data. I'm saying that whenever 250, 243, and 251 happens in this sequence, my next number will always be 252. This is given. This is post. This is prior information, right? This is from this data set itself. Understood? The first line is understood. Do you all of you agree to me? This is important, right? This is clear. Now my second line will be this part, okay? 243. What will be my second part? 243, 251, 252. Then my y will be 247. That is what I have written. If 243 and then 251 and then 252 happens, then my y will be 247. Clear? Right? So like this I can actually build. I have built my third one as well. Can you guys tell me what will be the fourth one? That will actually tell me what will be the fourth one. Okay. If you want, I can actually increase it. It's already at 166%. So what will be the fourth one? Okay. What will be my fourth one? The third one is 251, 252. So I will start from 252, perfect. 252, 247, 237, and then my y will become 244. Perfect, absolutely. So I can actually build like this, right? So now this is a sequence. I have transformed my tabular, non-interpretable sequence data into something like this which has relationship, and this is order. This is not something haphazard, isn't it? 252 has not come. You cannot just randomly shuffle this thing. There is a reason why they are like this, right? And this reason has been given by data, and you cannot defute data, isn't it? So now what we did is that we have transformed something into a sequence, right? This transformation is a very important idea. Please grab onto it, and you will see that it will work wonders for you. Two very, very important observations. Order is super important. You cannot simply zigzag things and go out of your way. You cannot. It has to be like this, right? So this order has to be preserved from this, right? And it is possible that there was a question, right? Y3, okay, Y3. You can do that, yeah. Is there a library you can do? Yeah. Many libraries. You can write your own library also. Okay, there are hundreds of libraries. In fact, moving average, if you take from moving average, right, there's a lot of implementation in that library itself. You can create data set. Sorry, folks, I'm just drinking. Okay, some more examples. So variable input. Now the thing is that some of you have said that Y3. No, it's like my explainer, my wish. But you can say that no, I don't want 3, I want 5. Now please tell me, what do you think intuitively if you use 1 versus 2 versus 3 versus 5? Which will give you what? If you choose 1, what happens? If you choose 1, what happens? Your data will be, so one will have 250 is my x, 243 is my y, 243 is my x, 251 will be my y, right? It might actually not be able to, you will not be able to generate enough time series information. Just one thing, right? If you do two is still reasonably okay, but anything above one is generally would make sense, right? And if you actually have a time window of one, it will become a normal regression problem, not a time series problem, isn't it? And if you actually do five, right? You can do five. You can also do more than five. You can do 50, right? How deep you want to be, how much history you want to carry, how much you said that no, my trend will be for 3 months based on my last 3 months trend. This is what it is. That statement, right? In this case, what will you say? You are the machine learning guy, data scientist. He is asking you. Remember that manager. So your response will be, after you actually build a successful model, you will say that based on the 3-day moving average, this is what I will say. Based on my 3-day moving average, based on my 3 days trend, you can't say moving average. Moving average is an algorithm, right? You are using neural network. You are way ahead. So you will say that based on my 3 days trend, I can predict this. So that depends on your data set, right? The thing is that one thing is very sure, the more depth you give to your sequences, the more information it has. But the only other problem is that if you actually create a data from a tabular to sequence, you're going to lose number of rows. Your example set will go down, right? So it should not go down so much so that you don't have anything to feed to your machine learning model, isn't it? Right? So you have to be also cognizant of that fact. Many a times you don't have millions or millions, or you might not have, right? But ideally, if you want as much depth as possible. A stock market guy will say anything more than three months is not required, right? But maybe someone says that I need whatever trend up to from 2 years only. You can own anything below 2 years, not acceptable, right? So that's up to the use case. You don't drop any outliers at all, right? While preparing the data, because this is the time information that has been given. Your objective is to, you know, build a machine in such a way that this time information is preserved, okay? And of course, you need to do some sort of regression because your output will be, number in this case, but you still need to worry about the fact that there is an order, and time and order is generally non-linear in nature, right? Why did 250 after 243 and 251? There is no set of combination. There might be, but there is no mathematical reason to be like this, right? So one day it can be just one, right? COVID has hit on that particular week, that will become one. What will you do? You can't, right? So there is non-linearity in case of sequence data. So you need to somehow imbibe that sequence as a feature, and this is how you can imbibe sequence as a feature. We will look into the one more example. It's a very common way of looking into language, right? If you have this, sentence, okay, this is one of my greatest sentence right now for last 24 months, is that I love teaching machine learning. So you have this thing, right? You can actually create a sequence like that. I love and then end with teaching. I love teaching and then end with, and then Y can be machine, right? I love teaching machine, then my Y can be learning, right? So love teaching, after that it will be machine, right? So love teaching machine learning, and you can say that there is a full stop here. I don't have anything else. So you can create a data set like this. Do you understand what I just did? I did exactly the same thing what I did for the numbers, with exactly the same thing with this sentence, right? And you will realize when you actually take the NLP course, or you go deep into NLP, now from this one sentence you can generate many X or many Y's and ask the model to learn language. This is a way you can learn language. It is not I love potato, it is I love teaching, right? So, and then that, okay, I teaching love is something different than I love teaching. Right? There's an order to it. There's a lot of things that you're trying to convey, and this is also one way to look at it. And not only that, you're also telling that there is also some sort of sentence finality or a full stop, end of sentence marker at this thing, right? So this is also a very common way of teaching extremely large, encoded machine learning models. Third line is nothing but like I love teaching machine learning, so I have a full stop, right? Full stop is important, right? In a sentence, you need to know when you're finishing. So machine also need to know when it is finishing, right? This full stops, commas, and all those things has meaning, right? Yeah, punctuators have some meaning, right? So you want the machine to also understand when to put a full stop, when to understand the full stop. TNN is just nothing but teaching an N, okay? I could not write the full form of T, that's it. T is teaching, M is machine, nothing else. Okay? T is teaching this word, M is this word, that's it, nothing else, okay? It was just not fitting in this, okay? So think like this is an extremely important understanding. Everything has to become sequence. And now if you have an X and Y, you have a supervised learning model, right? You have a supervised learning problem. Now it's in your game. You have some model, you have a supervised learning problem, you have a X and your Y. Now you are the king because you can build a lot, you can build a model. Somehow you will build a model because you are a machine learning guy, you know mathematics and X, Y, Z. You will build something out of it because now you are not only able to preserve the things, you are also able to preserve sequence which has order. It's very difficult, right? To how will you preserve an order? Will you put an order as a feature column? Very difficult, right? In videos, right? If you're taking a video, we discussed video yesterday. Do you think video is a sequence? Sorry, it's a data sequence of data. Is this a sequence data type? Okay. Do you think it's a sequential data? It's a series of images, right? A video, yes, it is. It's in fact, right? If you think about it, right? If it is multiple images, a particular image has to happen after that image. Then only it will become a proper video. If whatever video you've got, right? If it has 50 images, it's in some order. You cannot simply change the order and randomly and say that this is the video. Not possible. I mean, I'm saying technically it is possible, but you should not do that, right? That's the way, right? I love teaching machine learning. I love machine learning teaching. They're two different meaning altogether. It's not the same sentence. If I jumble up the words, it will have a totally different meaning altogether. It is not the same sentence. It's a different sample altogether. Hence, it's not the same video. Order is super important, and please realize this whenever you want to do sequential data. Okay. So and now that we need to know that, okay, till now we have never, yeah, few more, anything that everything is image only, right? Moving means like in a frame of per second, things are moving, right? So what I'm trying to say is that in our machine learning model, we don't know how to put a sequence of information. Do you know any model till now that you have learned that can take sequence of data? This is a sequence, right? I love, or basically let's take this 250 is actually an item. If you are doing normal software engineering, this is nothing but a list. In this list there are 3 objects. Each of these objects has some meaning and they appear in a specific order. That order has to be preserved, right? So this is actually a list of things in your, and it's not a metric. I'm not saying that it is a matrix. It's basically a list. It can be a matrix, but again a list, right? So till now, none of the machine learning model that we have done, okay, does take any sequence for that matter. Was it empowered to take any sequence till now? Do you remember any model that was taking any sequence? Any machine learning model or algorithm till now? Whatever we discussed, plus even in your, let's go back to traditional machine learning. Okay, if you know of anything, please put it. Okay, so that is what we are called as sequence data. Okay, right? So let's quickly look at it. Right, if you have a sequential data, so now let's look at it. The problem why. So you have this sequential data, right? This is my sequential data. Clearly 0.23, 0.72. And this is not 2 features, by the way, okay? Remember that. This is not 2 features. This is a sequence. So how will you compute a weight of this plus bias? So this will not be easy, right? The network does not remember. So this one, sorry, what happened? What is happening? Yeah. So the network does not remember what it gives and it just accepts the next data point. So when you have given 0.23 and 0.72 and after that 0.27 and 0.4 has happened, whatever network that we have learned, everything will be treated independently. It will do a forward pass, it will take the sample, it will go to forward pass, right? Forward pass will gives a bunch of weights and biases as well as loss function. You do the calculation of backward pass based on, based on all independent things, right? L0, L1, each of those losses will be computed separately, isn't it? So really none of the networks till now that we have gone can handle sequence data, because we have to somehow remember, or there has to be something that is there which actually connects these two things, right? That is not at all there. Okay, even in RCN also, one image at a time, right? You have not said that there is any kind of link between two different data samples, isn't it? Got it? So now, so let's go back to our explainer. So how, if that is what it is, so let's look, how do this is what we typically solve, right? This is what we come to know, right? We will, till now we are very good at CNN. Yesterday only we finished CNN, but before that we had dense layer. We had our X, right? We'll put via dense layer, dense layer, dense layer, and go to output, isn't it? Now, all these things are fine, but sequential nature of the data is not captured or even learned by this model. First of all, it is not even captured in the data. Even if it is captured in the data, suppose you somehow give this here, right? You can give it here. It's not that you cannot, right? But each of those, your forward pass and backward pass, by definition, the way that in the dense layer works, will not be able to capture this time, this component of sequentiality. Each of the samples of X are independent on its own, right? Each of the sample of X matrix is independent on its own. Clear? So we need a new type of network which can hold sequences, and it can do something. It can somehow link between these two or these three. In our case, what we did is that we did three, right? Why three? Maybe 30, right? So maybe it can link. So that sort of network which can link is called as RNN, and one of this linkage, okay, this linkage between examples is not a very hard link. It's going to be a soft link, right? You can actually treat this as a term called as memory, and it will make so much sense when we actually go through what is memory. So essentially what it will say is that in memory, you know that 250 has come for the first on the day one. After that 243 has come, and after that 251 has come from the memory, right? So this is some sort of memory which tells me and which guides me what is what, okay, and that is the power of recurrence, right? Recurrent is nothing but that itself. So we will be building an RNN or something called as a recurrence neural network. Recurrence means what? What do you mean by, in English, what is recurrence? Recurrence, right? Fact of occurring again, isn't it? The English definition says it all, right? Happens again and again and again. Proximity of happening again. So can we detect this recurrence using a network, and that type of network is called as RNN. Okay. Till now, are you guys with me? Means recurring. Yes, absolutely. Are we able to comprehend where we are leading? Are we okay? Great. Any obvious questions? So we had CNN, and in CNN we did not do that. We did not actually do functions of functions. I don't know why we did not do it. Maybe we should actually do that. How does a CNN convolution operations function does look like? Did we do? I don't think we did that, right? We have not expanded. Just the way we expanded our demo network, right? But what we'll do, like, we'll try to expand that function form here, so that it does gives us some sort of common sense understanding of how a framework, how TensorFlows will actually think about it, right? At least from a sense of it. So what is recurrent? Let me increase it. It's already abundant here, right? So recurrent neural network. So till now, recurrent neural network will take, it look like this, okay? It will have a block, and we will actually see what this block will look like. Okay, don't worry about it. This block will take the current term, okay, xt. When you say x might have multiple terms or items, right? How many items do we have? Let us actually get this data set here, because or else I have to again go back and forth, back and forth. Shall we put it here? Let's put it here. Now let's see. Okay. So how, in my x I have three terms, right? So I have three terms in my x. So at any time t, from the, so recurrence will take two inputs. So this particular network will take two inputs. One is an input for the current time step. Okay, this is called as time step. So if you pass it 250 from this side, and it will, you have to pass a previous memory. When you are passing 250, which is nothing but the first element in my x, there is no memory. You will start from 0. But we know that we don't start anything from 0, right? We will start with what? Which value we will start with? If we don't know what to start with, what will we start with? 1, is it? 0? No, we'll never start with 0. I mean, 1? No. There's something else we will start with. We don't know. It's called as random. So we will start randomly, isn't it? So the right answer is random. So you're going to pick a value and then you start with a random number, because you go back as part of your forward propagation and change those numbers. If you put 0, what will happen? There will be evidently in your layer will be some sort of multiplication operation, and you will end up with 0 itself, right? So that is the problem. And if you do 1, then basically all you're trying to do is like you're just doing 250 into 1 kind of thing. And we will see, right? Okay. How many sequences usually we try in a model like sequence? So there is, yeah, so that's a business call, that like how deep you want to go. Okay. So if you have an extremely large number of data, you can go, fairly big, right? But for a restaurant, for a hotel, I think 1 week trend is more than sufficient. They don't leave anything beyond that, right? Isn't it? So from our RNN standpoint, are we clear on what are the two things that it takes input? This comes in. This is a very important input called as a previous memory. Okay, what has happened earlier? Okay, and this is my current time item. So if I have three items, 250 will goes here. Okay, so structure of an RNN basically looks like this. Something happens internally, and then I will give you an updated knowledge of that particular item. Which item? Whatever item I processed. I process, in this case, if I process 250, then I will, this recurrent neural network unit, this RNN cell, will actually throw then updated memory called as ST. Okay? Clear? RNN's objective will be try to understand the sequence, and it basically takes two input. It will always have a previous memory and item in the sequence, right? One sequence is nothing but one of your samples. You might have multiple things. In this case, 250. You pass 250. You have to pass 250 from here. You pass the memory of 250 if you have, and the output will be, sorry, not the memory of 250, memory of the item before 250. In this case, nothing, right? And you will have an output of memory of 250. Okay? So let's be very clear on fairly. Are you able to understand this? I hope, right? So this is what it is. RNN node is nothing but it's trying to build this knowledge base, this ST somehow. Okay. If you want to apply our, this thing, let us see how it looks like. So we have three terms, right? Right? We have exactly three terms. So I have three RNN blocks. Okay. Think about it. So 250 goes here. This is my 250, right? This is my 250 goes here, and this is some random number, 0.83, some random number. Okay. Got it? Something happens here. I have got an updated number, or maybe this is 0.9. Okay. So this number is nothing but my memory of this particular 250. In the next sequence of my item, 243 will go. How much? What will go? 243, right? Right. This goes, and from the previous RNN run, I get my 0.9 is coming, 243 is going. So now what I will have a updated understanding, and this understanding is nothing but item for two. So I have one understanding of 250 and 243 occurring together. Think like that. Not only occurring together, occurring consecutively, right? And then the same operation happens. I will have an understanding of 250 comma 243 comma whatever, what number was that? That was 251 occurring consecutively, right? 251. So this is nothing but a knowledge of my t plus 1 and t plus 2 occurring consecutively together. So this is a very important. Remember, this is how I actually build the memory. Of course, after this we will have our, don't worry, so we will have our normal, what is that? Our dense layer, and then we can just directly submit to. So this is just some computation, right? 0.83 is nothing but a value, right? Everything is a number, right? What is everything is a number. All these things will be number, right? So I need to actually have a memory. So I will say that memory of an object here. What is the memory of an object? Which memory are we talking about? So 0.83 is not, 0.83 is just some number, some random number. Okay, I have to start from somewhere, right? I can't start from zero, right? Remember, if I start from zero, and whatever this neural network is doing, it will then definitely will be doing some sort of multiplication and summation operation, right? So we will start with some number. You can start with zero and you can see that. But my point is that this ST is flowing. This is nothing but it's generating some ST is, this is an output of this thing. Okay. No, it's not random. Next time onwards, no more random. So this ST is an output of this box, and we have not discussed what this box does yet. Okay, we will see that. So whatever this box does, it gives a definitive number now. No more heuristic. So if this box will do some summation and multiplication operation based on these two input, right? Just numbers, bunch of numbers. Remember, what does a typical neuron do? Does aggregation plus activation, right? Imagine that this box also will be doing something similar, right? And if it does, and it will give you a number. So it's total. This number represents whatever 250 is. Clear, right? Because the only data point that I've given is this. Everything else is nothing but weights. Everything else is nothing but weights, right? So how important this 250 is? Right now it is 0.9 times importance. Then it goes there and it says that how important is 250 and 243 consecutively appearing is whatever the value that it computes, right? So somehow it is continues this line, and this is how it continues to build the memory. Okay, let us get a very clear understanding in this before actually I expose what is this here. Are we able to understand and try it from an intuition standpoint? Are we able to understand from an intuition standpoint? We have some sort of memory network which is trying to learn as we go, and what are we trying to learn? This recurrence, that this consecutiveness, this sequence, and we are trying to model that sequence using our weights and biases. And what are we trying to say is that 250 is the item, and this is the importance of that number, importance of the memory of that number, and this is the memory of 253 happening before 243, or either way, 250 and 243 happening consecutively, whatever way you want to put. Okay, and you can continue it like this, right? There is no end to it as long as many number of. So now it's very clear, right? It's in a way it's intuitive that you can actually add n number of sequences, and your each network is literally learning each sequence, sorry, not sequence, each item in the sequence. Absolutely. It's aggregation plus activation. We have to do some sort of aggregation, and we have to do some sort of activation. Without this, a core of a neural network is not at all there. You have to put non-linearity, and we will see that there has to be some sort of non-linearity in each of them as well. Or else, it's a very linear operation, which will not work. So non-linearity only gives you that edge and that understanding and that feature, that feature learning, right? That is non-linearity is very important. Okay. Now that we understand this, I think it's about time for us to see what is inside this box, isn't it? Let us look at this box. It's a very simple box. Okay. This is what a box looks like. Okay. Each box will look like this. You can see what's happening here. Okay. This is exactly one box look like. So 250 goes here, and our some initial weight, right? Init weight. So this weight goes here, goes via dense layer, and this is only the dense layer, okay, without an activation function. So there is in this dense layer we have a weight. Okay, you can configure how many neurons you want here. Okay, when I say weight, it's a weight matrix again. So this goes via literally a dense layer, and my xt, my item in the sequence goes via a dense layer. That dense layer is also a list of weights. I do this aggregation operation. This is clear, guys. You can see this. This is a very familiar aggregation operation, right? Weight into the input plus some bias. Again, weight into weight into input plus some bias. In this case, I am adding a weight to my memory and a bias. And in this case, I am adding a weight, I'm multiplying, I'm doing a dot product with my input in the sequence and adding a bias. Once I do compute these two, what I do, I will do an aggregation operation, which is nothing but plus, right? And then I will run it via an activation function, tanh or ReLU. See, in RNN, I should not have written ReLU, but it's okay. I mean, it's not a problem because when RNN was done, it was all tanh, okay? But you can use ReLU also, it's not a problem. So, but the point is that this is the activation function. So, so the addition of these two terms value is run via the activation function, which gives the output. Okay, are we able to understand? Are we able to? So this is what an each RNN block looks like. Okay, from from intuition standpoint, it is not a it's straightforward, right? We were looking at each dense layer. In fact, we are looking at a neuron of each dense layer. In this case, you can say that 250 and this particular memory goes via some sort of dense, and goes via a little bit of weight matrix, add it up, run it via an activation function. When you run via activation function, you learn a lot of things. Okay. Without this one, everything will be linear, and there's literally no learning happens. Okay. Perfect. So in a sense that you can actually say that the function of st, if you actually think from a function point of view, is nothing but a ReLU. I'm saying ReLU or tanh, okay? Whatever the non-activation, whatever the activation function that you use, okay, this is ReLU of this weight plus this weight, the additiveness of both of these things. Now these two are constant, so in a clearer way, you will see this expression everywhere, okay? So for an RNN, a vanilla RNN, for an RNN, one second folks, okay. Can you see my screen? I think I have. For an RNN, what you can see is that this is the vanilla output of a RNN cell. Okay, are we clear? What we did is that so this is for one activation function. Now try to put this in the perspective of, before we put this into the perspective, let me actually copy this, right? Just for the sake of it, so that we actually have some common sense here. Let me just put it here. Okay, for us to understand. Okay, and let me just reduce this thing a little bit so that, okay, so it's easy for us to, okay, I can actually, oh, this there, huh? Okay, sorry. Okay, are you able to understand now? So now for our sequence has our sequence has how many items? Our one sample of my X has how many items? If you remember, do you want to see this? You can see there are 3 items. So for every item, I will do this operation. Okay, and there are 3 RNNs. So for every such item, the RNN will be run. It will do this operation. I will have an updated ST. Okay, that is at the crux of it, is what each RNN cell is. Okay, let's go back to the slides. Okay, sorry. Okay, let's go back to the slides. So before we go back to the slides, remember, now that we have built a function, okay, Now that we have built a function, so we can formulate this to our function of function of function formula. Okay, and there is, value in looking at. You can also build the computational graph out of it. Okay, because any of the frameworks or the mathematical aspect of it, they only think like this, right? You should also try to build a function of function for the CNN block. Okay, take a CNN block, put two CNN blocks and just do that. Okay, it will just be easier for you. You know why? Because then you will be able to understand backward propagation much better. That's all. That is one of the reason. Okay, so this is nothing but a function of function. All I did is that I just replaced all of my, this output is nothing but a function of this. Wherever I have S1, I have replaced with ReLU operation. Okay, if you have guys have any problems, so nothing to be shocked about it, or but this is just a function of function representation. I always do it. It helps me because this networks will quickly go really complicated. Okay, and sometimes it is easy. If I have to know what is happening in backward propagation of an RNN, it will be easier for me to actually deal with how many such operation functions that I have to do. That's all it is, right? So now the whole purpose of doing this is to do the backprop easily, because if you remember, we did this thing, right? So let's go back. So let's see what our, so this is exactly what I said. We have this weather data, and the data goes in and the data comes out. However, RNN goes via this feedback loop, right? Now, though here I am representing as three different stages, that is not exactly how it happens. It's basically I can actually run a for loop kind of a thing. Think about that, it's a for loop. Though it's still not a for loop, but at least it's just one cell, and you keep on feeding the same thing again and again, right? And not same thing, the next item again and again. Basically, it's just one network, right? But you first feed 250, then feed 243, then feed 251. Whatever is the output, you can get it out, right? That's the feedback loop. Perfect. Yes, that's the nothing but a feedback loop. Okay, if you want to. So data comes in, okay, and records a new state itself, computes that computation. Now you have a very clear idea of the equation of an RNN itself. One RNN is that equation. Okay, and just apply that equation. It's just a normal equation. It's no different than any simpler equation that you can have. Write it down, and then basically that's your RNN block. Okay, right? So this is exactly what we discussed. Data comes in, data goes out, and we can think of it as the state of the memory, or the memory that it's the data. What data comes out is nothing but the state of each of the item in the sequence. Whenever we say input, input is the whole X sample, right? Instead, you should think that you are trying to put item in the sequence. That is also called as time step. Okay, how much step that you are, how many steps that we have, right? So this is what uh, we can address that at the end of the session. Remind me, okay? Okay. So let's so just remind me. Yeah. So so let's see these things a little bit more detail. So we've got some x. Okay. Another way of representation. I was showing the x from down. This has been shown from side. Does not matter from which side it is, right? This only should give you an ability for you to comprehend different style of pictures, because a lot of people actually a lot of places it's explained in a different ways, but all of them actually mean same thing, right? So it's not bad to actually see the same representation from a multiple angles. So again, same way some weights is going, this is nothing but on x, then I have h previous, which is my previous state. This particular state is also called as my hidden state. Okay, so this is called as my hidden state, or hidden units, or basically it's called as hidden state. The memory is not called as memory, it's called as hidden state, and that computation that we have seen based on this goes here. Since there is only one RNN block, we will always give new access, or basically items in the x, and then it loops. Okay, that is what it is, right? So in this case, what we can think of it as, instead of, I don't, now if I actually now think like this, okay, do I really have to give the data like this, can I now take my original data, okay? Think about it, right? And just give it here. Oops. If I give my original data, do you think will there be a problem? Oh no, man, what is happening? So you're getting my point, right? If I give my tabular data, not this data, will RNN be able to handle it? Okay. Do you think the RNN will be able to handle it? So this is my day one. I just say 250, okay, and 243, 251, and so on and so forth, right? And then 252. So if I give the data as it is, my original data instead of my sequence data, right? I have not built a sequence. I just give it, right? So it seems that since I'm trying to build the memory, right, and I'm trying to use this block, it will be able to preserve the state, right? By virtue of using an RNN block itself will preserve this particular order of occurrence, right? Because you are trying to generate this XST, right? Understood? Is that clear? Are you guys with me? Okay, got it. So what do we two values are calculated, right? What are the two values? Two values are calculated in the hidden layer. The new or of the updated state, which are denoted as H new, and the output of the network is denoted. That is the end of it, right? Denoted at Y, right? So in a way that we can say that this is where actually tan H is what has been used. Okay, I just if you use TensorFlow or vanilla RNN block, um, I don't remember whether you can actually give a new, different activation function or not. I don't think you can, but we'll check that. Okay, I don't remember. So this is exactly the new. This is exactly what we discussed. H of new is nothing but some activation function wrapped around the weight on the hidden state, which is also called as memory or hidden state, dot my previous hidden state, which is coming from my previous time step, and add it with my weight of the x and my input. That is the final equation that RNN does, and that's pretty much about it. You can continue to do this, and at the end of it, so output of the hidden unit is simply calculated by multiplying, okay, that formula. After processing the first data point, a new context is generated, which is repeated until we actually read the until we actually get the output clearly. Okay, this is what an RNN looks like, and this is exactly what we depicted. That act of folding and unfolding is what I showed you. Okay, what happens is that you don't have different blocks of RNN as the number of things. You literally have only one net, but the items are being passed again and again and again. Think like that. Okay, so this is also one way to look at it. This is like, sorry. So you see this, the my RNN network, it keeps on feeding itself, and every time it feeds, it gets something out of it. Okay, and this is also one way to think that this is building the time feature, right? So it is actually what it's trying to do is trying to model that orderliness, right? In the from the data itself. Okay. So this is what we discussed. What is the typical functions? If you actually look from a function standpoint, right? So if you, this is your f of h prime, right? Which your h prime is the, h and h prime are the vector. So h is the current one and h prime is always the previous one. It is nothing but a function of current one given the previous h. Okay. This is nothing but the mathematical formulation on the formula. But we have a better formula, and which is something, if you actually look at it, you can do back propagation out of it. Because remember, everything is about x loss. Once we actually compute the loss, you see, you go here. Once we actually compute the loss, what I have actually taken an extra step. Whatever is it? I've taken an extra step and added a softmax also. I thought that this is a binary classification, some sort of classification, right? So I've added a softmax also and put a y. So this is actually, and then outside this there will be a loss function, isn't it? So this is a fully differential equation on which you can do back propagation and you can learn things. As with anything else, it is very clear. You are only seeing excess which you cannot change. Only in this case the problem is the thing is that there are more terms, right? You have lots of excess in the same formula itself, right? Earlier there was only one x, so this is lots of excess. But again, the whole fact of the matter is that these are all constants for us. You cannot change x. Everything, and if you expand s, s also is nothing but a function, isn't it? This should also be have been expanded. So everything is nothing but weights and biases against that loss function. So from our point of view, nothing changes. Now you might ask the question that how does this help? How are you trying to model this? How will this help? The intuition behind is that I am trying to generate a feedback loop and then multiplying the feedback loop with my input itself. This operation was always missing. If I remove this operation, it will just become a normal dense layer, right? If I add this operation, that is what this operation basically represents my timeliness or my sequentialness. So that is what RNN provides, okay? However, right, if you actually see, right, it is possible. Now remember, right, this is not tan, ReLU, right? Let me change it actually, okay? This was tan H, okay? This was tan H. So was this tan H, okay? I think RNN was done using, shall we just go there and actually let's look at RNN? I'm just curious actually. I don't know. So RNN on KRAS, okay? So recurrent base RNN layer. Let us open this, and it does not say anything about any activation function whatsoever, right? Which no, it was started with sigmoid. Sigmoid as a no. Acha, probably okay. I don't. So let's see. Do we the paper link will should also be here. Return sequence return. I was just trying to find out which is the activation. Okay, it's not written at all. Sigma. Okay, probably yeah. Tan is also the problem. Yeah. So we'll come to that, right? So the issue is that suppose yeah. So let's say this was sigmoid. I forgot actually. Okay, I think this is sigmoid, right? So either one of that. It started with sigmoid and tan H and went to ReLU. Now do you see what was the problem? The problem of sigmoid and tan H? Yep, you already said that. Both of them suffer from this problem of vanishing gradient. Why? Question to you folks. Why both of them suffer from vanishing gradient? Interview question. One is from 0 to 1, another is from -1 to 1. Because the range is too slow, it's very limited range, right? So your gradients will also, chances of having very low gradient is very high. If you have a network which is very deep, you will bound to see gradients diminish like anything, right? That was a big problem with RNN blocks, okay? And we will go through that in the slides, but that was one of the big problem with RNN blocks, okay? And it caused too much high instability, okay? The other problem was that it wasn't been able to handle if you have a really large sequence, like you want 20 or 200, I don't know. A language, right? Language model requires a lot of sequences, right? If this sequence of not 3, you wanted to use, there was a question, right? Not 3 but 30. RNN will fail miserably because it was not able to hold too much of this memory, this S, right? The S, what it is were doing, it was not able to hold so much of memory. Okay, the final number that it represented was not that much solid, which represents, a really deep sequence. Basically, in the easiest term that you can say, it can't remember for too long. Okay, who can, but at least RNN cannot. That was one of the feature. That was one of the problem with RNN, but it sort of helped a lot of algorithms to come through, but RNN, you know, had this problem of vanishing gradient. Let's come back to this. Okay. So it has a problem of vanishing gradient. Okay. Let's look at very common aspects, applications of RNN, shall we? This is a very common application. What is this? Speech to text, right? Speech to text is what? By the way, speech to text is what? Till now we have not. So when you speeched, you said something, the data is in sequence. What format of the data will be? Data. So till now we have done sequence to, you say you got the sequence and you said that, you predicted a value. But in this case, this particular speech recognition application is what? It's a sequence to sequence model. No, I'm trying to say that your data is also coming in sequence. You are also outputting sequence, which means your data is coming in sequence, which we have understood. The model is also outputting a sequence. It's a continuous stream of things that is coming, right? So that is that is something that one has to understand, that it is. So we were till now we were dealing with from basically one data point to another data point. Then we have dealt with in the morning sequence to data point. Now we are talking about sequence to sequence modeling. Can you give me one more example of sequence to sequence? Very common example. Translation, absolutely, yeah. It's nothing but a classical sequence to sequence problem, right? Translation is definitely you start with some language, it's a sequence, and give it in a different sequence. Perfect. You can image captioning, okay, is also a sequence to sequence problem. What's an image captioning? Do you think this is I don't know, is this a sequence? Sorry. You can create a model that is capable of understanding all the elements in a image. Okay, so this is not a sequence to sequence, right? So, but this is basically one to image. Your input is nothing but the image, right? And you have to say that this is a woman, this is a cell phone, this is purple, this is crowd, camera, whatnot, cat. I don't know where is cat, but cat, and so on and so forth, right? And you know, so yeah, so how do we do it is a different thing, but can you imagine, just if you have to imagine, forget about everything else. Can you imagine how you want to do it? You have this image, and the first part of network will be what? What will be the first part of network, which is not written here? It will be a CNN, perfect, because you need the features, right? It will be a bunch of CNN networks, and you will grab the features, and once you have those features, you will you will have some sort of classifier, right? And then maybe from there it actually goes to a RNN and the data comes out, right? So image captioning is different than image classification, right? So this is also like, what do you see in the image? Have you seen that? You have seen the other way around. If you say something, it generates the image. Have you gone through that model? DAL-E. It's one of the famous now. It's a generative model right now. It can create any image if you actually ask it to create an image. Check this thing, DAL-E. And there is an open, Hugging Face has open a URL, and you should actually look at that. Okay. So that's also a sequence to sequence model. Okay. Sentiment analysis. What is this? Is this sequence to sequence or something else? You give a bunch of reviews. You'll say that whether generally it is good or bad, isn't it? You give a bunch of. So it's not a sequence to. It's a sequence to. Perfect. It's basically sequence to one, many to one. This is also called as many to one to many. But I would like to think from a point of view of naming them sequence, because then I can wrap my head around what my data generally will look like. Okay, and this is also very common problem, right? Sentiment analysis, spam classification, right? Spam or not spam, right? It's a sequence to see. Nowadays, it's a sequence problem. It's very common, right? Spam detection was a very popular use case of naive-based algorithm. Okay, and there's a lot of real life application has happened till the time everyone was started getting millions of emails a day. Right? Till the time people were getting 5, 10, that's fine, but then everybody in the whole world was getting billions per day, and that's a different ball game altogether, right? So yeah, so that's also a sequence to a class. It's a classification problem, but input is sequence, and your classes will be one. And we will actually look at this sentiment analysis. We will look at it in our assisted practice whenever we do it. Okay. So now that we have gone through the basic structure of an RNN, anything which is deep is good. We said that, right? We have understood that. You can put hundreds of RNN blocks. We have put many, many CNN blocks. VG16, ResNet 152 layers of CNN, right? And operation, convolution, N. So you can do that as well. You can create recurrence, right? So smaller network is generally difficult, right? If you have an extremely large number of that, this is anyway a problem. If you have very large data, right? If your X is very large or your total number of sample size is large, the fully connected layer, shallow fully connected layer never will be big, right? It will become big only, right? Because you're think about it, for every such RNN, how many neurons are we talking about? That is anyway configurable, right? But at least there are two networks. For every time there are two networks minimum, right? We have two networks which is running, and this is configurable, right? You can say that dense of 64, dense of 64. The weight matrix can be 64, isn't it? For every such item in the sequence. That's a lot, right? So that is something that we have to worry about. But it's possible to do. We can also construct bidirectional RNN. Okay, this is an interesting thing. If I actually go here, right? Let's just go to that language problem. Where was our language? You can say that I love teaching machine learning. When you go from the left to right, okay, the meaning is for you to understand. It's very clear. Now it also so happens that this side also has a meaning, right? Because if you know both sides, you can maybe able to construct or predict the sentence much better, isn't it? It's very intuitive, right? So if you do one side versus if you do both side training, that you would actually learn a lot more than what is expected, right? So that is generally called as a bidirectional RNNs. Okay, you are learning from both sides. So that way you can flip these things. That okay, if you have learning machine, then teaching will be your why. Okay, if you have learning machine teaching, then love will be your why. If you have learning machine teaching love, then I will be your why. Okay, and you can teach the machine in an inverted sequence itself, and this is also a sequence, right? So both this sequence you can concatenate, so that okay, then you can okay, then it is easy for the machine to say that, okay, it's not only this side on my right to left, I also my left to right also validates what I'm now learning. Okay, so bidirectional RNNs are a popular construct. Okay. Of course, deep RNNs, right? We have extremely deep RNNs by adding more layers of a simple RNNs, right? RNN on its own is a very simple block, but we can add more RNNs, right? We also have something called as a pyramid RNNs. This is called a stacked RNN. You can build on top of it. Well, the lower layer can be RNN, bidirectional RNN. After that, you can put a one more layer of normal RNN. Then on top of that, you can put one more layer of bidirectional RNN. So this is nothing but how much deepness you want to provide or quantify your network with is what is up to you, but you can do this thing. This is called as stacked RNNs. Okay. However, the deep RNNs, as we discussed, are sometimes it is very hard to train, but also usually it doesn't remember data beyond certain time steps. When we say doesn't remember the data, that means the score that, sorry, the memory or the hidden state that it comes out of it is no more representational of the number of sequences that you wanted to remember. Okay, then that score matrix, or that hidden state matrix, or the memory matrix that it outputs has, it's deviated from the, it doesn't it's not a representation of what it should be, right? Hence it affects. And this is, initially it was all good, but so maximum it can bidirectional in RNN, and for deep RNN we can put multiple. You can put, yeah, absolutely. You can put multiple bidirectional array, bidirectional RNN. Okay, you can actually stack them on top of together. Okay, and you can do a lot of things. That is, the model dot sequential is on your head, on your time. You can add anything there. Okay, but yeah, when you do it, you generally should have a rationale behind it. Remember that. Okay. So what was the problem with RNNs? The biggest problem was this idea of vanishing gradient, and the one easy way to actually look at it, the problem arises while updating the weights. Okay, if you actually unravel this, Z is what? Where is Z? Where is Z? Z on what are the inputs output, right? X1 goes function, Y1 goes function. Why are we doing X, Y, Z? So that we don't confuse ourselves and we have some index, right? That's all it is, right? These are all inputs and outputs of each of this block. Each block is nothing but a RNN block. It has an input, a hidden state, and then that whatever the output of that block is goes to Y, and then another RNN, and so on and so forth. Okay, it's just that one output. So what was the problem? I want to show you why this vanishing gradient is caused. Okay, I want to ask you why. So you answered me with one, saying that because of the uses of the tan age activation layer, that RNN used to suffer from vanishing gradient, which is partially true actually. Okay, so sigmoid, right? The use of sigmoid, which is partially true. The other reason is that if you do eventually somehow, you know, do able to backprop this equation of a typical RNN, you will see that ultimately, if you simplify, mathematics is all about simplifying a complicated equation, right? So you can simplify this equation and do differentiate it while doing back propagation, and in fact while applying that particular chain rule. Remember, when we apply that chain rule, you will see that lots of values will be just weights multiplied by weights multiplied by weights. Okay, multiplied by weights. The same weights getting multiplied many times. Okay, so this can also cause of exploding gradient, and then it's also cause of staticity. Right? There is nothing to learn. No new W is coming out of it. That is also one of the reasons. So if you do eventually do the backward propagation of this particular equation, you will see that it's very apparent that the weights diminish, and I think that is important reason of vanishing gradient than the usage of our activation function. This definitely contributes because all these RNNs are nothing but hidden layers, but I think the backward propagation was more of a killer. Even if we change this to ReLU, so that's one of the reason of putting it. Now I remember why I had put it. This was some time back. Even if you change this activation function to ReLU, this problem, this kind of network, will still be causing a problem here with your vanishing gradient because of the back propagation of this equation. Okay, even if you change this to ReLU, you will still not be excused from the fact that typical RNN will have vanishing gradient, and because of the back propagation of this particular equation. Okay, just wanted to point out that. Okay, that is what it is. So vanishing gradient was an important step, and before we'll not go there now. So what we'll do is we'll take a short break. Okay, and 15 minutes, not more than that, please. So there's some questions. What is it? H and 0 are two parallel RNNs. Perfect. Absolutely not parallel RNN. So this is H and 0. Yes. No, H is a hidden state. So this is this is stacked RNN, right? Or you can say deep RNN. We have one layer of RNN, same RNN, right? F1 is one RNN. So F1 and F2. Not H0. H0 R0 is, where is R0? So it's an H0G0, right? You said H0G0 are hidden states which are going into the RNN F1 and RNN F2, right? So this is RNN F2. So you can have multiple RNN layers. Yeah, G0. I understood that. Don't worry. So you can have multiple RNN layers. Just like you had multiple convolution layer, remember? You can have multiple RNN layers. Your objective is to go deep. You can go deep. You can add n number of layers. But the problem was that while RNN was good, what we will see now is that while RNN was good, it did not, it fueled a lot of things, okay? And while when the networks were, going, all it did, so networks were exploding, right? So with like lots of data, and because of that problem of this, I will explain to you when, if we actually do end up having that backward propagation class, okay, maybe I can explain to you what was happening there, okay. So my take is that even if you change this particular activation function inside each RNN block to ReLU, the property that there is vanishing gradient will not go away, okay. So that was my understanding, okay, and that's because of the back prop. When we come back, we will see that, okay, sorry, I don't want to. So we will see that there is an improvement on top of RNN, which is called as this term called as LSTM, and LSTM's approach is very similar to what we approach, the way we build our memory. We actually do four operations every time we build memory, and that operation is very synonymous to someone who's working with a database. Create, read, update, delete, CRUD operations. Four CRUD operations, okay? It's like we always create new things, new memories. We frequently read and access them, right? We update our memories very frequently whenever we see there is find a chance, and we delete or drop what is not needed. So we will come back post break and we see that how RNN, sorry, how LSTM, whose full form is long short term memory, long and short in the same sentence, okay. So long short term memory revolutionized the whole thing in such a way that whenever someone says that, if someone says that in a question that I hear that, hey, I am using this RNN layer, he's actually meaning that he's not using the vanilla RNN that we discussed. He's actually using an LSTM layer. Okay, 99.99% he's using an LSTM layer. So whenever someone says that he's using RNN, which is nothing but an LSTM layer. Okay, nobody right now uses a vanilla RNN anyways. They will go to LSTM. So we will just give a high level overview of what does LSTM does, how does it handle this vanishing gradient problem, more importantly, how does it handle this long term memory, how can it, that memory problem that RNN was facing with, how did it do it, okay. Let's take a quick break, come back, 15 minutes, okay guys, work for us. Thank you. Okay, our 15 minutes are over because we started 2 minutes earlier. And yeah, so shall we start? Shall we regroup? Maybe people are still thinking 2 more minutes. So meanwhile, does anyone have any question on projects? I'm really interested to actually know that, if you guys have actually started and what kind of problems that you are facing. That will basically give a good idea of where you are in your learning journey. Okay. The projects are quite big, in the sense that the data set is big. They are not toy data sets, isn't it? We have seen, right, one of the data set was actually 300,000 records. So yeah, I think quite big. So, I know that some of you have said that it's gonna take off, you're gonna attempt on over the weekend, but I think that you should start discussing, at least maybe get prepared for something on Friday. Okay, Friday's session, let us discuss something so that you will have, if you go through, at least go through the data set. Okay, and have a mental plan. If you have any questions, we can clarify on Saturday, on Friday's session, and then on Saturday, Sunday, if you want to attempt it. For those who wants to attempt it over the weekend. Okay. Otherwise, I think it's what's going to happen is that at the you will do it in a way, or maybe you'll not might not be able to finish it. Okay. So I would strongly urge you to actually go through all of the projects. There's quite a bit of assisted and unassisted. Are you guys independently running them? Whenever you have time. If you're not, please do that. There's only one way is to, while it's okay to actually see videos and, other resources, but the thing is that please understand that, this is still programming, and doing is the best way to actually get your hands dirty. Okay. So what should we do? So we have, let's look at this. Let's actually look at, before we actually go to, so let's look at what sort of use case that we are supposed to do. One is there are two practice. There are two assisted and one on unassisted. Okay, none of them on RNN. All three are on LSTM. So I would imagine that the way this is planned is that let's complete LSTM, and maybe then we can actually attempt these things, right? Other way is to, let's look at RNN layer itself. Keras documentation is very detailed, and you can actually look at the way RNN layer is actually built or called. This is a very typical way. LSTM also looks very same. Okay, you have cell state, you have sequences, return states. By default, they don't return it, but you can ask for it. Okay, and these two are important parameters. Okay, the sequence and state are important parameters. When you actually go deep into NLP, you will see that there are many sort of applications can be solved via this RNN layer itself. Okay, shall we start LSTM? Any obvious questions that we want to ask on RNN, or I think let's start LSTM? What do you think, guys? Shall we start LSTM? Yeah. Okay. So what was the problem that that RNN suffers with? It suffers with this problem, right? Of so RNN suffers with gradient instability in terms of vanishing gradient, and of course, and which is basically vanishing gradient results in the way the output of vanishing gradient is that less learning, which is nothing but in a way that you don't have too much memory. The final state that the RNN layer gives doesn't actually remember for too long. Okay, so we need to solve this thing, right? So how do we solve it? We've solved with this new age um, class or a model architecture called as LSTM. And the way we'll do it is that a way typically we build our memory is using four operations, right? And what is those four operations? The four operation is nothing but create. We create a lot of memories. We create through experiences, and we store those created ones. And we frequently use them whenever we want, right? And we should have an ability to access them very frequently. Then we also update those. It's not a one-time thing for us. We'll actually update our memory. If we make a mistake, we go back and update the memory, right? And also we delete or drop things that we feel that is not needed. So one of the reason RNN doesn't did not work is because it is trying to do all of this in one shot. Okay, it was trying to do all of this with that concatenation or summation operation from based on output of two dense layer. Okay, so LSTM, what it attempts is that it uses different networks for different memory operations. So for all of these things, it uses different network. Okay, there's a very popular Chris Colla's article. Okay, understanding LSTM. I would suggest that don't go it now. Maybe go a little bit later after you understand it. It's really beautifully written. Okay, and it's one of the popular articles that you can find out of from LSTM. Okay, so what happens now? Let's look at what does LSTM do. Does again remember every time what are we trying to do? We'll create, we'll read, we'll update, we'll delete. Okay, these are the four basic memory operations that LSTM will perform. What RNN was trying to do, RNN was basically concatenating two dense layer in the hope that all of these operations were doing it at one shot. However, LSTM will use different network. The sound of it itself tells us that it's a complicated network. While it may be complicated, but it's easy because we do it on a daily basis, right? This is how we read stuff, learn stuff, and we store our memory, most of it, right? Fair enough. So now let's start with the first intuition. Okay, either the intuition number one is that there are two types of memory we are talking about. Okay, two types of memory, right? RNN used to have one memory state. LSTM has two memory state. There is something called as long-term memory, which is called as a cell state. Okay, and suppose this is your cell state. This line goes as a cell state. Another memory, which is nothing but a short-term memory. Okay, this is not team. This is term memory, right? It's called as a hidden state. Okay. Okay, are we on page? So do you see the importance of C and H? Do you see do you see we also do this? We have a long-term memory, a very long-term memory, like go back to years and years, right? And we have a very short-term memory, right? In our long-term memory, there might be things which has impacted us are there, some things which has not impacted us in some way are dropped. But in our current context, the hidden state or the current memory, like whatever we were doing in last 6 months is like really fresh, right? So that is the first intuition that LST. Let's start with that intuition. So we have a C and H. These are popular notation. H is nothing but the hidden state. This was the only hidden state that we had in RNN. C is something that we have added now. Okay, think about it. Okay. So now we have a long-term memory as well as short-term memory. Hence the hence the name long short-term memory. Okay. I don't know why they forgot to put an and, but for whatever reason, it is long short-term memory. Okay. So the first thing that happens is that I need to actually delete things that I don't need. So I will create LSTM has the first network which is called as a forget get. Okay. What it does, it makes a list of things to forget, and while it forgets, it also keep things, right? because just said, okay, no, this I don't want. I will do a delete operation, and consciously also I will keep few things. When I do a delete operation, it also means that I will not do delete operation on some other things. So the act of remembrance is nothing but the act of forget is that do the delete operation on some, and act of remember is that don't do the delete operation on some other. It's as simple as that, okay? So what are the things that you have to do? You have to first make a list of items that we have to forget, and that basically remember. Basically, we have to make a list of items to forget and remember. This is entirely based on my previous hidden state and my current input. Whatever my previous hidden state was, whatever my previous short-term memory was, and whatever is my current input, that will dictate me what I want to forget and what I want to remember. Okay. So the output forget gate, it is the name as per the paper was called as FT, will only have values from 0 and 1 because of this sigmoid operation, right? Between 0 and 1, which basically means that, you know, it basically means that this input, it basically if it is 0 means you are gone, right? This particular input is not needed or this state is not needed. So how does the network looks like? It looks almost similar to that we have for the RNN, right? So this is basically one dense, two dense, and of course we have weights here, right? The weights are associated somewhere here, right? Remember that whenever we have dense layer, you will have weights, right? So you have one dense, two dense, second dense, an aggregation function, then you have a sigmoid, which is an activation function, and you have an output, okay? So this output goes somewhere. Right now I am not showing this output goes where, okay? For now, let's assume that output goes somewhere, okay? All right. So this is my first network, okay? This network is nothing but a forget gate, okay? And in our computer science we have these gates, right? And or gate, right? In our gates or gate, all the things, you send some signals, something comes out, think like that, okay? And this terminology is directly from the paper itself and is generally accepted, okay? So basically you have given a hidden state, previous hidden state, and you have given the input step, current time step. So if you remember our example, we have passed 250 in the sequence of 251, 243 and 252. I have given my first time step, which is 250, and my previous hidden step. It can be starting, if it is starting, it is random. Do the dense activation. Dense, what will be the dense? Weight dot input plus some bias is an output of a dense layer, and weight dot xt plus some bias will be the output of this particular dense layer, and you do a summation operation, right? Pass it via sigmoid. This looks so much like a RNN electron, right? Doesn't it look like almost like an RNN? This looks like an RNN, right? Okay. So this is the first thing that it does, forget gate, okay? What is the third intuition that we have to do? We have to build something called as LSTM input gate, okay? We have now, what do we did? As per our model, we deleted what we don't want and we've remembered what we want, okay? I have deleted that I don't want to know, how to write code in R probably, okay? Sorry. But I have refreshed every time I give a session, I refreshes my memory on machine learning, LSTM and so on and so forth. So that's what I do, right? So this is my first network that I built. The second network that I built is input gate. I will now, what it does is that this particular gate makes a list of things to add and update. Critical, right? These are new things that we have to add, right? So this is the input gate. So what items I have to add and what items I have to update are based on again my previous state and hidden current input, right? These are the only two things that I have. I don't have anything else. Okay, the output indicates what I want to update, goes to my long-term memory. Okay, So we can use a ReLU here. Sigmoid is always generally used in forget get. I don't remember whether we can change it. I don't think we can change it, but we can use a ReLU here. Okay. And this particular input get also ensures that you just don't blindly replace everything to long-term memory. You selectively do something. Okay. These are very basic intuitions. Okay. And we can always come back to LSTM. LSTM is one level up. So this is the input get looks like. How many networks are we talking about? Can you guys appreciate the network's depth? It's not there's not depth, but the complexity of the network. Okay, complexity of network is not. This is my forget get, if you remember. Okay, right? So the network is like this. This is my input. So I have hidden step, current timestamp, input, hidden step, current timestamp. So this whole thing is my input gate. Don't think that even if this network looks very similar to my LSTM forget gate, it's actually a copy and an independent network just to support LSTM input gate. Okay. So the reason is that so this whole operation is nothing but adding and updating. Remember that, right? How it happens? So this is very simple, right? This branch of my network will tell me what to forget, right? What to do, right? This is my LSTM forget gate, right? And so this will actually allow me to stop things to update in my cell state, which is my long-term memory. I will show you how cell state is joined in all of these things. Okay. For now, just push hidden state, push current timestamp, do an aggregation, go via tanh. You can actually use ReLU in this time step. Okay. And just before updating this information to my cell state or my long-term memory, ensure that just validate it once with forget get, because don't take everything to cell state. Okay. We are done with two networks. We still have one more network. Okay. So we have somehow managed to complete two network called as forget get and input get. So let's come to the final network, which is nothing but my LSTM output gate, and this is where I expose this line called as cell state. Okay, cell state is something that goes all through the line, and this is FT is nothing but my forget gate. This is the output of my input gate. Okay, so this gate is the output is nothing but IT to multiplied by C, and FT is my forget gate. So one more time, this whole of the network is actually under this FT. This whole of the network of LSTM input gate is under this summation. And this cell state is this long-term memory. I'm continuing my long-term memory, right? So what I did is that I multiplied my long-term memory with my forget gate. Whatever continued, let it continue and come here, right? Whatever is gone will become 0, right? So which means you have already deleted from my forget gate. You have applied a forget gate on your long-term memory, right? After that, from my input gate, what you did is that you updated, you are adding, you are doing addition operation, right? Or updation operation, either way, to my long-term memory. You might have added a new stuffs, new values, or you might have updated some existing values, both, okay, to my long-term memory. So after this, my long-term memory is ready. It's like an aggregation, but think from an intuition standpoint. If you actually go to maths, right, it's very easy to actually lose yourself. Not for everyone, but most of us can actually lose ourselves. But think from an intuition, and then you can actually build this long equation. Okay, once you actually build the equation, if you can, you will be able to actually back propagate, right? And then it will become easier. What I'm doing is that forget gate is ensuring that remove from long-term memory, which is my cell state. This long line called as C is nothing but my cell state, and my input gate ensures that if I have a new value, add to the cell state, and it also ensures that if there are some existing value that I have to update, please do update that. By how much or by how much is a question of later computation on gradient. However, I'm still not done. This is called as an output gate. I need to have an output, right? what will be my output? I will have two outputs. My output is already being given by this. One is my cell state output. Another is also has to be my hidden state output. We said, right, LSTM learns two things: long-term memory and short-term memory. Though my long-term memory computation is done, I still have to compute my short-term memory. So what I do, I will again pass a hidden state and an input state. I will pass this via forget get style network. This is exactly like forget get style. I will multiply my long-term memory, pass it via an activation function to bring some nonlinearity, multiply with a value from my forget get. It is possible that some things from my cell state, which is my long-term memory, will translate into hidden state, which basically reflects where am I right now, whatever is happening in my current thing. Whatever is very old, it will not come translate to my hidden state. Okay, little complicated, mind blowing, I know, but it's from understand from an intuition standpoint, I think you'll get a hang of it. Okay. So how many? So this is my hidden state. This is also an output. Okay, this is an important output. So now, if we actually join all of this together, this is one LSTM cell looks like. Okay, literally, how many networks are we talking about of one LSTM cell? Forget gate, input gate, output gate. So this is 1, 2, 3, 4, 5, 6, 7, 8. Right. So one LSTM cell has 8 blocks of dense layer, and each of them can have multiple layers. These are all dense layers, right? So I can actually have, I can specify that forget gate will have 64 units. So each of these will have 64 units, right? And that's how deep. That's one. This is one cell, right? So this is. But the good thing about this is that I'm learning each operations to update a memory on its individuality. I don't have to muddle like RNN to learn one shot because I'm not there yet, and it might be very difficult. So this is the network that I follow, and whole of LSTM cell looks something like this if you actually apply our problem. Okay, so this box, same box, replaced with RNN with this box. Earlier in RNN we had two dense layers. In a typical LSTM, I think there are two more LSTM layer if I'm not wrong. They are called as forward or reset. Sorry, reset is in GRU. I think there are two for. I'm not sure. Okay, I forgot actually. But there's definitely eight dense layers. Okay, to start with. With this LSTM cell, yeah. So this one, this is a joining of everything. What is happening is that this is I've understood. I have told you guys individually all of it. So what is happening is that we started with my a basic cell state, right? This is my long-term memory. I've started, so whatever I am at time step t, right? Currently I am at time steps t. So I've started with my cell step, the previous cell step, right? So now what has happened is that apply my forget gate. Whatever is coming from my previous cell state, start from there. Try to forget whatever is in your long-term memory. You have to ensure that don't carry forward you have to forget and delete things which you want to, and remember only those things which you do not, which you want to, right? Delete which you don't want, remember which you want. So that can only be achieved by this operation. This operation from the value that you come out from the forget gate. The forget gate multiplies with the value of previous cell state, and here you have what the output of this operation is nothing but some deletion of cell states which you don't need, and that's about it. And some things will continue to be there. So which means whatever is flowing in is basically means that you need those. Okay, they are good memories to continue, or good, in other words, memories are good. They're good values, right? Ultimately everything is number, but they are good numbers or memories to continue in the network, right? That's the first operation. Once I have a good sort of values of my from my once I have a good set of values from my previous cell state, I will now try to update my long-term memory, right? My objective is now try to update my long-term memory. How do I update my long-term memory? I use this is my input stage. Okay, this is exactly my input get. If I do this operation, what happens is that at the end of it, my cell state will be added with new values which I want to update, so which I want to add, and some existing values might also get updated. So I will get a fresh C. Okay, at this point I have got a fresh C. This is what I have. I have got a CT. So after I have started with CT minus 1, after this to operation, I have got a fresh CT. Okay, that is what I. How do I do it? I use this input get. What is input get? Input get uses four layers, two independent layers. One layer looks like forget get, which we keep, which we ensure that we don't, and another layer is also like forget get, but using as tanh layer. Okay, and it says send the same stuff when, and it multiplies with this, okay, with the my forget get kind of a layer. What it does is basically only passes on things that we want to add or update, nothing else. So my cell state, my current cell state is perfect. Okay, it is what I need right now for my this current time step. So if I pass I'm passing, where am I passing? I am passing 250 here, right? I am also passing 250 here, right? and and this is my old one. These two are my old values, right? And this is also I'm passing 250 here, right?